Welcome to Podcast Learn and Fun. Let's start today's journey of learning. Have you ever wondered how the universe works at the smallest level? Like what's really going on with atoms and particles?
It turns out it's a lot weirder than you might think. Yeah, almost like the universe has a whole set of hidden rules.
So like a secret code.
Yeah, kind of. One of the most mind-blowing concepts in quantum mechanics is this idea that energy, it's not this smooth flowing thing, but actually exists in like discrete chunks, almost like a staircase instead of a ramp.
So you're saying energy is like those old school video games where everything moves in like blocky steps.
That's a great way to visualize it. We call this quantized energy,
Yeah.
and it has huge implications for how everything from atoms to light behaves. Imagine a tiny particle, like an electron, trapped inside a box.
Okay, I'm picturing a subatomic billiards table. What happens next?
Well, this particle can't just have any energy while it's bouncing around in there. It's limited to very specific energy levels, just like climbing the rungs of a ladder. These energy levels are determined by the size of the box and some fundamental constants of nature.
So the electron is stuck on this energy staircase and can only be on certain steps. It's so bizarre.
Exactly. And this staircase analogy applies not only to particles trapped in boxes, but to atoms and molecules as well.
Hold on, so the electrons in atoms are also on an energy staircase. How does that even work?
It all comes down to the way quantum particles behave, you see. Their energy levels are determined by the forces acting on them. In atoms, it's the attraction between the negatively charged electrons and the positively charged nucleus. That's what sets the allowed energy levels. It's like the atom itself creates the boundaries for the electron's energy staircase.
Okay, so it's not a physical box, but the forces within the atom define the electron's energy levels. My brain is starting to hurt, but in a good way.
That's a great way to think about it. Now, to describe these particles, we use something called a wave function. It's basically like a heat map showing us where the electron is most likely to be found.
So it's not like we know exactly where the electron is, but we have a pretty good idea of where it could be. That's a little spooky, but it makes sense.
Precisely. And for a lot of systems, the solutions to the equation that governs these wave functions don't actually depend on time. These solutions describe what we call stationary states, where the probability distribution of the particle stays the same over time. In other words, the electron has settled into a specific energy level on that staircase.
So it's found a comfy spot on the step and is just vibing there.
You could say that. Now, the shape of this wave function, or the electron's comfy spot on the step, directly determines the particle's energy level.
It's like the shape of the step dictates how much energy the electron has.
Oh.
That's wild.
Yeah. It is. And this is where it gets even more interesting. Due to the nature of the equation that governs these wave functions, combined with the fact that particles have to be confined to specific regions, like an electron in an atom, only specific energy values are allowed.
Wait, so you're saying the energy of a particle can only be certain, like, discrete values? It can't just have any energy it wants.
That's right. It's back to our staircase analogy. The particle can only stand on specific steps, not in between. We call this quantization of energy.
Okay, my mind is officially blown.
Yeah.
So how does this quantization actually work in the real world? We talked about boxes and atoms, but where else do we see this?
Well, one of the most striking examples is how atoms interact with light. You know those neon signs that glow with vibrant colors?
Yeah, they're awesome. What do those have to do with quantized energy?
Those colors are a direct result of those quantized energy levels. When an atom absorbs energy, its electrons can jump up to higher energy levels, like taking a step up on that energy staircase.
So it's like giving the electron a boost of energy, and it leaps to a higher step.
Exactly. And when those electrons fall back down to lower energy levels, they release that energy as light. It's like they're sliding back down the staircase and emitting a burst of light as they go.
Okay, that makes sense. But why do we see different colors?
That's the really cool part. The color of the light, you see, it depends on the difference in energy between the two levels that the electron is jumping between.
So a big jump means a different color than a small jump? It's like the electron is playing a giant xylophone, with each step making a different note of light.
That's a fantastic analogy. And because each element has its own unique set of energy levels, like a unique xylophone, it will emit a unique spectrum of light when its electrons make these transitions. This is why different elements produce different colors when heated. Their electrons are jumping between those quantized energy levels, releasing energy as photons of specific wavelengths.
Whoa, so those beautiful emission spectra that scientists use to identify elements are all thanks to quantized energy levels.
Precisely. Now, this quantization of energy isn't just about pretty colors, it's also the reason why atoms are stable.
What do you mean? How does quantized energy keep atoms from falling apart?
Oh, imagine if energy weren't quantized. Electrons could continuously lose energy and spiral into the nucleus, kind of like a ball rolling down a hill with no bottom.
That doesn't sound good for the universe.
It wouldn't be. But because energy is quantized, electrons have a ground state. The lowest energy level they can occupy, like the bottom step of the staircase, they can't go any lower than that, so they stay in a stable orbit around the nucleus.
So it's like the universe has built-in safeguards to keep atoms from collapsing. That's amazing.
It is. This whole concept of quantized energy is not just some abstract theoretical idea. It's absolutely fundamental to how the universe works at the most basic level, and it has real-world implications for technology, too.
Oh, really? Like what?
Well, take lasers, for example. Their operation relies on the fact that atoms can only emit light at very specific wavelengths due to those quantized energy levels. We're essentially harnessing those electron jumps to create those focused beams of light.
So lasers are basically just carefully choreographed electron jumps. That's mind-blowing. What about other technologies?
Solar panels. They work by absorbing photons of light, which bump electrons up to higher energy levels. We can then use those excited electrons to create electricity.
Wait, so we're literally using quantized energy to power our world. That's incredible. I had no idea this strange concept had such practical applications.
It's truly remarkable. And the deeper we dive into quantum mechanics, the more we realize how essential these concepts are to our understanding of the universe.
I'm starting to see that. So what's the big takeaway from all this talk about quantized energy? The big takeaway for me is that the universe is a lot more bizarre and counterintuitive than we tend to think.
It certainly is. One of the biggest challenges in quantum mechanics is reconciling this strange behavior of the quantum world with our everyday experiences, you know?
Yeah, it's like our brains are wired to think in terms of smooth, continuous processes. But at the atomic level, everything's choppy and discrete. It's almost like the universe is pixelated, not smooth and continuous like we imagine.
That's an excellent way to put it. And it's this pixelation, this quantization, that gives rise to all the amazing diversity and complexity we see around us. From the colors of a sunset to the way our brains work, it's all ultimately governed by the laws of quantum mechanics.
So even though we can't directly observe these quantum phenomena in our everyday lives, they're constantly at work, kind of behind the scenes, shaping the reality we experience.
Absolutely. The quantum world may be hidden from our direct view, but its effects are all around us. And the more we learn about it, the more we realize just how profound and awe-inspiring it truly is.
Well, this whole conversation has been a real eye-opener for me. It's made me realize there's so much more to the universe than meets the eye, and it's definitely sparked my curiosity to keep learning and exploring.
That's fantastic to hear. Keep asking questions, keep challenging your assumptions, and never lose that sense of wonder.
I won't. Thanks for being our guide on this incredible journey into the quantum world.
It was my pleasure.
Thank you for listening to Podcast Learn and Fun. If you like our videos, please subscribe, click the like button, comment, and share. See you next time.